Hello students, and welcome to Topic 6 of Alternative and Renewable Energy Sources. The topic we will be covering is the design of solar photovoltaic systems. Not all the energy produced by PV modules becomes usable. A percentage is lost due to mismatched modules, equipment losses, and other losses. These losses are known as the derate factors. Derate factors are given here. These derate factors are from PVWATTS. Nameplate derating of 0.95 means there is some variation in the actual output of a PV module compared to its listed rating. No piece of equipment is 100% efficient. Therefore, inverters, load controllers have derate factors. There is also loss of energy due to mismatch of modules. The least performing module will reduce the output of the other modules. Naturally, we are familiar with energy loss of electrical wiring. There's also loss due to soiling, system availability, and shading. Shading is a special topic which we will cover later. The module performance is affected mainly due to changes in irradiance levels, operating temperatures, shading effects, and other correlated factors. The power output varies significantly with any deviations from standard test conditions. Not all of the modules exiting the production line have the same output. They are tested and collated. This means some have a higher than average output and some have less. Inverters, transformers, controllers are not 100% efficient. Therefore, they heat up during operation. This is a loss of energy. A default derate factor of 0.92 is common. As stated before, modules exiting the assembly line do not all have the same output. These mismatched modules may be placed in series with higher performing modules. This acts like a weak link in a chain. That series will perform at the level of the lowest performing module. Diodes to block or direct the flow of electrons and connections all add electrical resistance and add inefficiencies. We're all aware that wiring in an electric circuit adds electrical resistance, heat, and inefficiencies. Both DC and AC wiring adds resistance and inefficiencies. Soiling can be an important factor in the performance of modules. Dust in locations with little rain can reduce the module's output significantly. Module output reduces with age. This is probably due, in part, to increased resistance in connections. Shading is covered in slide 13, is a special case and can reduce module array production significantly. A shading analysis must be completed on any site with shading. There are analytical methods to determine the estimated reduction in production. We will be performing these calculations in our next lesson. This slide lists the steps involved for the designing of a standalone system. The first thing that must be done is to estimate the electric load. There are various ways to do this. The best way is to use existing utility data. After the load is estimated, it's time to size and specify the battery bank. Sizing and specifying the array usually comes next. After the battery bank and solar array have been sized, it's time to size the mechanical equipment, such as the controller, the inverter, and the wiring. Households do not usually use the same amount of electricity month after month. The availability of solar resource is also not consistent month after month. This all must be taken into account with the design of the standalone PV system. When designing a standalone solar PV system, it is necessary to conduct a critical design analysis. This is outlined here. The battery bank must be designed for the month in which there is the most electricity use. The array must be designed for what is termed the critical month. The electrical use in the home is not consistent throughout the year. The solar resistance that is available is not the same throughout the year. Therefore, it must be determined which month has the highest use with respect to the available solar resource. This is referred to as the critical month. Here is introduced the fact that the horizontal tilt angle of an array will affect the monthly output. If the tilt of the array with respect to the horizontal is flatter than the local latitude, the array will produce more in the summertime. If the tilt of the array is higher with respect to the local latitude, the array will produce more in the wintertime. The table has 3 columns to record the solar production at the tilt angle less than latitude, at latitude, and greater than the local latitude. This is compared to the average daily electric use. This slide shows us a typical monthly electric use for a home. In this case, we would design the batteries for the highest use month, which is 45 kilowatt hours per day. This slide gives the first 4 steps in designing the battery bank. This slide gives the remaining 4 steps in designing the battery bank. And this table is used in calculating the size of the battery bank. After the battery bank is designed, it's time to design the solar array, as outlined here in slides 22 and 23. We must first divide the design amp hours per day by the estimated battery efficiency of 0.8. We then divide the peak sun hours in the critical month to obtain the required peak array amps. We then must select the PV module. We divide the required peak array amps by the maximum power point amps of the module selected. This will give us the required number of modules in parallel. We then divide the system voltage by the nominal voltage of the module to obtain the required number of modules in series. Multiplying the number of modules in parallel by the number of modules in series will give us the required total number of modules. This table we use for designing the array So let's do an example. In this case, the individual electric appliances and lighting are added to obtain the design average AC load. The tabulation of the AC average load is 3,527 watt-hours per day. These are the design specifications of the desired system. Voltage, DC voltage 48, days of autonomy 4, depth of discharge 50%, choosing a 6-volt battery with 350 amp hours. The module, the PV module, has an 85 watt power, has a nominal voltage of 12, has peak amps of 502, that's the peak power point amps, and short circuit amps of 5.34. The PV module will be mounted at latitude, and then there's a controller and the inverter specs. The table here is used to design the battery bank. We will enter the AC average load of 3,512. We divide this by the inverter efficiency 0.9 and by the system voltage 48 to arrive at the average amp hours per day of 81.6. We multiply the average amp hours per day by the days of autonomy, divide by the discharge limit of 0.5, divide by the battery given amp hours of 350 to arrive at 2 batteries in parallel. We divide the system voltage 48 by the voltage battery of 6 to arrive at 8 batteries in series times 2 batteries in parallel gives us a total of 16 batteries. We will next design the array. This example is a special case in which the electric use is consistent every month. This is not usually the case. As the electric use is inconsistent for every month, it is consistent for every month. It is only necessary to determine the month with the least solar resource. In this case, it's the month of December and is 4.1 peak sun hours per day. In this table, we will be performing the array calculations. We will again use the 81.6 amp hours per day. We will divide that by the default battery efficiency of 0.8 and divide by the peak sun hours of 4.1. This gives us the required array peak amps of 24.9. We then divide the array peak amps by the maximum power point amps of 5.02, which gives us 5 modules in parallel. The system voltage is 48. The nominal voltage of the module is 12. We need 4 modules in series multiplied by the 5 modules in parallel gives us a total requirement of 20 modules. This is a layout of the system we just designed. Let's now design the required number of modules for a grid-connected system. We do not need to consider a critical month when we design the array for a grid-connected system. Usually, a grid-connected system is designed to produce no more annually than your annual electric use of the home. This is stated here. Looking at the peak sun hours on this table, we can see the monthly average peak sun hours is 5.4. We will use this value to design our grid-connected array. We will use a different method, as outlined here, to design the grid-connected array. If we look at the equation, we see that the output of the module multiplied by the derate factor and the peak sun hours and the number of modules will give us the required watt hours per day. Rearranging the formula and making it explicit in N and entering in the appropriate numbers leads us to the required number of modules, which is rounded up to 10. If there are any questions, please post them on eLearned Help discussions.